the the first module, okay, under which we'll be learning about belt and rope drives. Okay, so belt and rope drives, you might have noticed in many of the machines. Even you have worked with the lathe, right? You might have noticed how the power is being transferred from the motor to a machine. Okay, so in especially in the lathe, and even you have noticed the power uh, chain drives, belt drives, rope drives. Okay, so these are the things you might have noticed. So based on that, we will be learning about. Okay, we come to the hoisting tackle. So this is one of the example of a pulley mechanism, block and tackle mechanism. This is used in lifting the weights. Okay, so there are two kinds. Okay, when to raise the load and to lower the load mechanisms. Okay, so in the hoisting tackle, as we have seen one of the hoisting tackle just now. Okay, so it consists of a two pulley blocks, one above the other. Okay, it consists of a two blocks. So on the upper block is there, then one more is there, the lower or the bottom block. Okay, upper or the top block, or the other one is the lower block. Each block has a series of sheaves mounted side by side on the same axle. So you can see the sheaves or the pulleys are being attached on the same axle. Okay, as well as bottom as well as the top blocks, top and bottom blocks. Okay, the ropes are used for in a hoisting tackle are cotton ropes, hemp ropes, and manila ropes. That's what I was just discussing. So here we can use cotton ropes, hemp ropes, or manila ropes. Okay, so it is a non-metallic kind of ropes that are being used in this kind of hoisting tackle. The pulleys are manufactured in two designs, fixed pulley and the movable pulley. So there are, as I was mentioning, there are two designs in the pulleys. One is a fixed pulley and the other one is the movable pulley. So this is what we have. Okay, so coming to the it's working where Q is the load to be lifted. Okay, so you can see here in the sketch. So the upper top block and the lower bottom block. Okay, so this is the one. Usually the upper will be fixed, the lower will be moved up and down. Okay, it depends on how you lift the weight. So Q is the load to be lifted. You can see in this mechanism Q is the load to be lifted at the bottom. P is the effort required to raise the load. So this is the effort what you have to put in the rope. Okay, so nothing but a force we apply. So you have seen the how a person or a man who lifts the tons of weights of logs. Okay, in just just 1/10 of the effort at the rope. And n is the number of pulleys or sheaves used. Okay, so whatever the number of pulleys you use will be represented by the number n. T1, T2, T3, etc. are the tensions in the rope. Okay, T1, T2, T3 are the tensions in the rope. C is the pulley coefficient or a constant or a ratio of adjacent tensions. Okay, you can tell that it is a ratio of adjacent tensions. We can see here in the sketch. Okay, you can find the upper pulleys and lower pulleys, and you can see the tensions in the belt. If P is the effort that you put at the one end of the rope, and the other end of the rope is fixed to the upper top block, and whatever the tension you get here because of putting an effort at the other end of the rope, Okay, so then we take that as a T1 on the first end to the other sheave end, first sheave end. So that is taken as a T1. The next tension in the rope is taken as T2. Similarly, other T3, T4, T5, T6 as shown in the figure. Okay, so these are the tensions in the belt. Okay, so what we do is we just calculate the condition, the effort required. Okay, or nothing but a q we calculate that there are two conditions to raise the load. First condition, what we do is we just calculate the ratio of tensions in the belt, ratio of tensions in the pulley. Okay, I mean to say the rope. Okay, so raising the load in the block is pulled downwards at P. This is what you do. So we use the ratio of tensions. Okay, so C is equal to T2 by T1. Okay, tight side by the, this is the ratio that we use. Okay, for raising the load. Okay, for raising the load. So T2 by T1. So adjacent tensions, ratio of adjacent tensions in the belt. Okay, for raising it becomes T2 by T1. Okay, similarly for the other ratios you have T3 by T2. So this is how you can write the equations. Okay, at the last you have whatever you have is the P by T6. So there are six ropes connections you will get in the rope. Okay, so the final ratio is P by T6. Okay, so this is how you get the ratio of belt tensions. I mean the rope tensions in the um, hoisting tackle. Okay, then you can rewrite these equations in the form of T1, T2, T3. Okay. Now I'll write the first one, that is ratio of tension in the T2 is given by C into T1, which you can get it from this ratio, right? As you can see here, T2 can be written C into T1 as shown. Okay. Similarly, you can write T3. T3 is equal to T2 C in, okay, C into T2, which is nothing but your C2 C square into T1. Okay, C square into T1. Okay, so similarly you have T4 is equal to C T3 is equal to C to the power 3 into T1, and C T to the power 5 is equal to C T5. Similarly you can write in terms of T1. You can write in the terms of T1. Okay, so this is how you get the ratios. P is equal to C T6 is equal to C to the power 6 into T1. Okay, so this is how you get ratios. Okay, so this is what you get. Now coming to the equilibrium at the lower block. Okay, so you can write Q is equal to, okay, so Q is equal to T1 plus T2 plus T3 plus T4 plus T5 plus T6. So there are six connections are there in the rope, drive, hoisting tackle, and you can rewrite these in terms of T1, T2, T3, T4 and T6. So now we have seen how to write the tensions in terms of other tensions. So T1 as it is, T2 in terms of ratio of tensions into the initial tension is T1. Similarly, C to the power 2 T1 plus C to the power 3 T1, C4 to the power T1 plus C5 to the power T1. So this is how you get, and you can rewrite these in terms of T1 into the root of, in the bracket you can write 1 plus C1 C plus C square plus C cube plus C to the power 4 C to the power 5, like this you can write. So which is nothing but a geometric progression, right? So you can write this summation of this geometric progression in terms of the the equilibrium q is equal to t1 into c to the power 6 minus 1 divided by c minus 1. So this is what you can take. Okay, is equal to p divided by c to the power 6 into c to the power 6 minus 1 divided by c minus 1. Okay, so this is how you can write the equilibrium q at this end. Okay, so at the lower block. So q is equal to you get q is equal to p by c to the power 6 c to the power 6 minus 1 divided by c minus 1. Since t1 is equal to c to the power 6 into t1, or you can rewrite t1 is equal to p by c to the power 6. Okay, so this is what you have done it in the previous steps, right? So p is equal to c to the power 6 into t1. So you just replace that and you get the effort required to raise the load. You can rewrite this equation of q, okay, in terms of p. So what you get is here p is equal to, so this p you get q into c to the power 6 into c minus 1. So that is what you get in the numerator, and in the denominator what you get is c to the power 6 minus 1 as shown in the equation. So you get a equation to raise the load is equal to p is equal to q into c to the power 6 into c minus 1 divided by c to the power 6 minus 1. So this is how you can uh, get the equation. So this is for there are 6 pulleys. Okay, this is for the combination of 6 pulleys. If there are n number of such pulleys, then wherever the 6 that you need to replace with the n. Okay, so now we can write q into c to the power n into c minus 1 divided by c to the power n minus 1. So this is how you get the equation for calculating the number of pulleys, I mean to say the effort. Okay, the effort required at the end of the pulley can be calculated by knowing the q values, nothing but sum of the tensions, and n is the number of pulleys used. Okay, so if you know the number of pulleys, you can calculate this effort required at the end of the lever. Okay, so that's what we can calculate. So this is when you want to raise the load. Okay, when you want to lower the load, then the equation will little changes. Okay, this is how you get lowering the load. What you get is like this. So for lowering the load, the block in the same way we do, okay, in the lowering also. So instead of that putting the effort at p, what we do is we just loosen it. Okay, so we can rewrite the coefficient of the tensions in the way as shown. It is c is equal to t1 by t2, t2 by t3, t3 by t4, t4 by t5, t5 by t6, t6 divided by the p. Or else you can rewrite these ratios in terms of t to the power t6 is equal to c into p, t5 is equal to c into t6, t6 is equal to c to the power 2 into p, T4 is equal to C3 to the power P. So everything you can write in terms of P. Okay, everything you write in terms of P, or equilibrium conditions. What we have, Q is equal to T1 plus T2 plus T3, T4, T5, T6. Okay, so this is what is that you have to do. Okay, so Q is equal to T1 plus T2 plus T3, T4, T5, T6. Okay, this is the equation we use. So now you just replace the T1, T2, T3, T4, T5, T6, and in a similar way you can calculate P into C and to the into C to the power 6 minus 1 divided by C minus 1. It's similar. So in the similar way you calculate the equation which is required to raise the load, or you can rewrite P in terms of P, nothing but effort at the required at the to lower effort required to lower the load is given by P is equal to Q into C minus 1 divided by C into C to the power 6 minus 1, or in general if there are n number of um, this one if there are n number of sheaves or pulleys, then you can write wherever 6 you just replace with the number of pulleys n. So it becomes P is equal to Q into C minus 1 divided by C into C to the power n minus 1. So this is how you get the equations, okay, for lowering the load as well as to raise the load. So these are the two things you should remember, and usually they will ask this in the exams. So coming to the types of V belts, we have almost 7, 8, 9 types of belts. We have endless V belt, assembling V belt, narrow V belt, wide V belt, narrow V belt with cogs, double angle V belt, great angle V belt, V band, pro lip belt. So these are the types what we have in the V belt. Okay, so usually we in this case, okay, in our syllabus it is an endless V belt that we use for the most of the calculations. So these are the type of V belts that we have, but only one type of that is endless V belt. We use it for the calculation for the syllabus. So what are the advantages of V belt over the flat belt? So advantages, if you can see, compact and will give you high velocity ratio, and it provides a shock absorption between driver and the driven shaft, and it's a positive and reliable drive. Because of the wedging action in the grooves, the loss of power due to the slip is less. There is no joint problem as in the case of flat belt drive, which is a joint drive. Here it is an endless V belt that we use, so there is no problem of joints. So these are the 5 advantages of a V belt over the flat belt. We can look into the disadvantages. So the initial cost is more, as a fabrication of pulleys is a V grooves is complicated. So you need a mold like thing to get the, the trapezoidal V cross sections, and it cannot be used when the center distance is large. So it is for the small center distance, say 1 meter, 1.5 meters maximum. So that is a one disadvantage. So improper belt tensioning and mismatching of belt results in reduction in service life. So that is a one more disadvantage. So tightening, mismatching, and of the pulley, I mean the belt over the pulleys will lead to the reduced service life. So these are the disadvantages of the V belt. So coming to the ratio of belt tensions for the V belt or rope belt drive. Okay, this is the equation that we use. So for the flat belt we use T1 by T2 is equal to e to the power mu theta. Okay, but in case of V belt, what we use is T1 divided by T2 is equal to e to the power mu theta divided by sine alpha. So this is the extra thing that we have, where theta in radians, alpha is in degrees. So we can see what is this screw angle. 2 alpha, what we can see is the groove angle of the belt drive. So if you can consider uh, the tension in the belt, T1 minus Tc divided by T2 minus Tc is equal to e to the power mu theta divided by sine alpha. So this is how the equation changes when you consider the belt tension in the ratio of belt tension equations.